Good morning and thanks for watching. I'm Terje Røllevåg, and today I'm going to show you how you can use a digital twin, that means a FEDEM plugin, in order to calibrate the path generated in IGUS iRC. The main objective with this calibration process is to calculate a path which consider the flexibility in the structures and gears and the loads acting on the real robot. As you probably know, IGUS iRC and most other path planning tools are using pure kinematics, while FEDEM is a nonlinear finite element program that incorporates all dynamic effects. So the process is as follows. First, I program the TCP path in IRC. Then I use the inherent inverse kinematics in IRC to calculate the joint path. This joint path is transferred to FEDEM via CSV files, and then I can simulate the true TCP path and hence also the TCP deviations in FEDEM due to the flexibility and the loads. And then I can use these deviations to update the TCP path in IRC. And again, I'm using the inverse kinematics to calculate a correlated joint path. Then I can run the FEDEM model through this correlated joint path to document the improved accuracy, or I can load it to the real physical IGUS robot to document the same improvement. In my benchmark, where I used 4 reference points, target points, I improved the target point accuracy with 97 to 100% in all directions. While I'm running this FEDEM simulation, I can also output stresses and strain time histories, which I can use for fatigue analysis, and that is running much faster than in real time. In this video, I'm using a Python and Streamlit program in order to execute the IRC and the FEDEM software. But that is only for demo purposes. In a real implementation, I would export the FEDEM model to a FMU, which I can use as a plugin in the IRC software. This slide is showing the process in more technical terms. First, I program the TCP path, which is a rectangular pattern with 4 target points in IGUS iRC. And then IGUS iRC is calculating the joint trajectory by using the inverse kinematics, and it can also output the kinematic TCP trajectory. Then I can simulate the joint trajectory in FEDEM, and I can calculate the true TCP trajectory. And then I can calculate the TCP deviations, because FEDEM is considering all the flexibility effects and the inertia loads and gravity loads acting on the real robot. And when I have these deviations from the TCP trajectory, I can run them through the IRC inverse kinematics, and I can calculate perturbations to the joint trajectories. And then I can add them to the original joint trajectory in order to calculate the correlated joint path. And then I can execute the corrected joint path in FEDEM once more to document the improved accuracy. Or I can load them to the real physical robot to document the same effect. And in this benchmark, I was able to improve the accuracy in the 4 target points with 97 to 100%. Here you see the FEDEM Digital Twin model. And as you can see, each part is meshed with a dense mesh and assigned the correct material properties. And each FEM component is coupled together with the others by using joints and gears with the correct properties as well. In addition, I added these blue symbols, which are virtual strain gauges that can output the stress and strain time histories from hotspots on the robot during operation. I could also add control system, but in this example I run the FEDEM model with the joint angles which are calculated in IGUS iRC directly. The mass and stiffness distribution of the digital twin model was validated by both static and dynamic tests. I used load accelerometers to verify the eigenfrequencies of the robot, and I used this digital plunger to calculate or calibrate the static deflections due to gravity, and the accuracy was 0.1 millimeter. The model damping was also validated by dynamic tests, and here you can see how I can execute the real physical robot from my Streamlit Python script. And please watch the resonances that the robot has during the benchmark, the rectangular pattern. And as you can see, I added a payload on 1.5 kilos on the TCP of the robot, which are used in all benchmarks. And here you see the LORD software that I used in order to measure the vibrations and hence also calibrate the damping. And here you see the output to the web application. In FEDEM, we use Rayleigh damping, which is mass and stiffness proportional, and that enables me to tune the damping at two different eigenfrequencies. So here, for example, I added 5.2% damping at 6.3 Hz. The final model validation was performed in one of NTNU's robot labs. And here you can see the dynamic performance being measured continuously by fine instruments. You can also notice the oscillations due to resonances that occur when I have this 1.5 kilo payload mounted on the TCP. Here you see the validated FEDEM Digital Twin model running through the same rectangular benchmark pattern. The red curve here is showing the kinematic TCP path, and the green curve is showing the FEDEM simulated TCP path, including the contributions from the elastic displacements. And here is roughly a deviation in the target points of 3.8 millimeter in the vertical direction. We can also see that FEDEM is calculating the hotspot stresses in 6 virtual strain gauges simultaneously, and it runs faster than real time. During this simulation, FEDEM is also calculating the strain and stress time histories in 6 different virtual strain gauges. And this is performed 4 or 5 times faster than the real robot is moving. FEDEM can of course also be used in order to run full finite element analysis. And this can be used in engineering. So if you want to get rid of certain eigenfrequencies in the robot path, you can simply scale the individual FEM components and see how that affects the overall structural stiffness of the robot in different positions. So FEDEM is an excellent engineering tool for IGUS engineers. So let's step through the process. You start by programming the TCP trajectory in IGUS iRC. And this is based on a pure kinematic calculation. So this path is perfect, does not consider any flexibility, gravity loads of the real robot. And while IRC is running this path, I extract the joint angles which I use in the FEDEM simulation, which is the next step. When IGUS iRC has calculated the TCP path and the joint paths, you can import the joint path to FEDEM using CSV files. And then you can simulate the true trajectory in FEDEM. The red curve here is showing the kinematic path, and the green is showing the FEDEM calculated path. And as previously said, the deviation in the target points are roughly 3.8 millimeters in the vertical direction. Then the next step is to use the TCP deviations in the 4 target points calculated by FEDEM to update the TCP path in IRC, and then recalculate the joint path. The final step then is to use the calibrated joint path in FEDEM to document the improved accuracy. Or you can simply download the updated calibrated path to the real physical robot. And here you see this is how the robot performs after the calibration. And here you see that the kinematic path and the FEDEM path is very much aligned. And the maximum deviation now is roughly 0.1 millimeter in the 4 target points. This slide is showing the TCP accuracy before and after calibration. The blue rectangular pattern is the kinematic pattern calculated by IRC. And the red pattern here, the trajectory, is the one calculated by FEDEM. And you can see there is a deviation in this Z direction, and it's in the range of 2 to 4 millimeter. However, after calibration, the deviations are used in combination with the inverse kinematics to calibrate the joint trajectories. And then you can see that the TCP is hitting the 4 target points with very high accuracy. And the accuracy in this case is improved by 97 to 100%. Between these 4 target points, there are still deviations. And these are due to the non-linearity of the robot and the eigenfrequencies. In this example, we only see the YZ projection. We don't actually see the oscillations because this is not a time series plot. But in principle, I could have calibrated and eliminated the eigenfrequencies between these points. But then I probably had to use a notch filter in combination with direct access to the inverse kinematics. However, without direct access to the IRC software, I can only calibrate the accuracy in the target points. And here you see the numbers which shows the improved accuracy, especially in the gravity and the sideways direction. And you see that the maximum deviations are reduced from minus 3.7 millimeters to 0.1 millimeter. And if you calculate the percentage reduction in deviation, we are in the range of 97 to 100%. In this video, I used the Streamlit and Python program to execute FEDEM and IRC. But that is not how this should be implemented in a real application. If IGUS wants to improve the accuracy of their robot, they could simply export an FMU from FEDEM. And an FMU is simply a kind of zip file with the solver, that means FEDEM, the digital twin model, which is the model I showed you, and predefined inputs and outputs defined in an XML file. And the inputs are typically the joint angle trajectories, which are stored on a CSV file or directly streamed. And the outputs from the FMU would typically be the stress or strain time histories from the virtual strain gauges, the TCP path, and the TCP deviations. And this FMU is a standard, so it can easily be plugged into any digital twin framework or offline programming system like IGUS iRC. So the main message to IGUS and commonplace robotics is that you can simply plug the FEDEM FMU into IRC and improve the IGUS accuracy at all target points. If you want to improve the IGUS accuracy in the interpolated points, I need access to the inverse kinematics and we need to control the eigenfrequencies. To do so, we can use FEDEM as an engineering tool to optimize the stiffness of the IGUS robot. Finally, I would like to inform you about FEDEM. It is a nonlinear finite element program that was initially developed by NTNU and SINTEF back in the early 80s and 90s. Then it became an independent software company that was acquired by SAP around 2015. Then FEDEM was transferred from being an engineering tool to a digital twin monitoring tool. And FEDEM has traditionally been used by many robot companies like ABB Robotics, Neos Robotics, Syntax Factory Automation, Sandvik Coromant, Cincinnati Milacron, and ESA as well. So FEDEM is an excellent engineering tool, and it's also now an excellent tool for improving the robot accuracy. If you want to learn more about FEDEM, you can visit my homepage track.no. There you will find a download page where you can download papers describing industrial implementations of digital twins, and you will also find papers describing the basic FEDEM technology. You can also visit my YouTube channel, where you will find FEDEM playlists with training videos and also digital twin implementations in different disciplines. And after SAP pulled out of the digital twin business in 2024, they made FEDEM open source. So now you can find FEDEM software, the source code and the executables on openfedem.org. So now everyone can download the software for free. Okay, so I really hope that you found this video interesting. And if you like to see more videos on how to improve robot accuracy by using digital twins, you should subscribe to this channel, because I will post new robot videos where I use FEDEM as a plugin to improve the accuracy. And here you have the contact info. So hope to see you again. Thanks for watching.